Hello everyone. It's been a while I have uploaded my videos. Today onwards, we will start a new course called Linear Algebra. Myself, David Raj Michael. I'm working as an assistant professor right now. I'm interested in teaching the mathematics through coding, but this course I would mostly concentrate on pure mathematics than the just coding. Anyway, I'll be using my coding knowledge to help you understanding through some figures. So this course is basically for undergraduate and postgraduate mathematics students. Some of the engineering students also can follow the course, although we will be dealing with all the vectors and other linear transformations, etc., through mathematical point of view. I would also like to show some of the applications of application part along with the theoretical aspects. So, what are we going to cover in this course? I have splitted this course into 10 modules. Module number one is vector space. In this, we will cover what is the vector space and basically what is a vector, and then followed by what are the subspaces and cover properties. And then uh, model number two is we'll discuss basis and dimension. In this, we will discuss the linear independent set. What do you mean by dependency of two vectors or linear independency of two vectors? And then linear span of a particular given set. And then basis of a vector space, dimension of a vector space, and some of the properties. And similarly, module 3 has linear transformation. In this module, we will cover the algebra of linear transformation, its properties. It has been widely used by engineers as well as any of the science background people. Matrix representation of linear transformation we will discuss, and followed by we will discuss something called linear functionals. We will define what is linear functionals, and we'll see what about the annihilators and its properties. And the fifth module is the eigenvalues and eigenvectors. In this module, we'll discuss the eigenvalues and eigenvectors, characteristic polynomials, minimal polynomial of a given matrix or a given linear transformation, and then we'll prove Cayley-Hamilton theorem in this section. We'll also discuss diagonalization and necessary and sufficient condition for the diagonalizability in this area. Module number 6 contains invariant subspaces and triangulability. We discuss invariant. We discuss a set which is invariant under a linear transformation, and of course, the necessary and sufficient condition for triangulability of a linear transformation will be studied in this portion. Module number 7 will have decomposition. We will not discuss all the decomposition, but we will discuss direct sum decomposition, along with that, we will discuss the primary decomposition theorem, and then cyclic subspaces, Jordan decomposition theorem, etc. Module number 8 contains inner product spaces. In this, we'll discuss a notion called inner product and a notion called norm, which is induced by the inner product, and then orthogonality of a subspace, and then orthonormality, and then there we will discuss the orthogonal basis, orthonormal basis for a given vector space, and then we will discuss the Gram-Smith process, which helps us to uh, find an orthogonal or orthonormal basis from a given set of vectors. Then module number 9, we discuss the self-adjoint operators, adjoint operators, and as a special case, we will discuss some of the normal and unitary operators, and then we will also discuss the spectral theorem for self-adjoint operators in this portion. And finally, module 10, we will discuss the bilinear forms. In that, we'll also discuss the skew symmetric and then symmetric bilinear forms and group preserving bilinear forms. So we have a full-fledged course to cover here. So the 10 modules will engage you from the 0 to the higher level of linear algebra. So this course is being taken for a fundamental course for linear algebra, which means the people who would like to have any further topic in which follows by linear algebra, something like functional analysis or metric spaces. If they want to study any of the courses, this course will become a preliminary for them. Throughout this course, we will follow linear algebra by Kenneth Hoffman and Ray Kunz as a textbook, and We also follow linear algebra by Serge Lang as a reference book, and also we'll follow linear algebra by Friedberg as reference book. Okay, so this is a course overview. Anyway, I'll see you in the courses. Thanks a lot.